Okay. Okay. So today our goal is to continue towards forward kinematics. You remember last time what we discussed was transformations of bases, right? And the goal was last time was to acquaint you with how we do those basic operations, right? How we do those basic operations. To give you an idea of how to transform vectors from one basis to another. This time, we'll apply this knowledge to work with vectors, work with forward kinematics. Okay. You'll see as we go what I mean. But if you think about real robots are, 3D. They don't exist on a plane, as examples in the first lecture. So this is a part of our picture. Now we lift now we lift assumptions. And again, our goal is to try to describe their kinematics. Okay. Okay. Now we still start with quite a theoretical view on this stuff. So first, let us just consider a vector v. Okay, let's just consider vector v. As we discussed last time, we can express it in terms of coordinates of v. Okay. So we can describe it in terms of coordinates. To describe its coordinates, we need to have a basis. Okay, so we need something that would give us a basis that can be used to generate those coordinates. Okay. Okay. Alternatively, we don't have to write it in terms of its coordinates. We can just leave it be, right? Is also a viable option. But if you want coordinates, we need a basis. Okay. Typical examples of vectors in robotics include linear and angular velocities. Okay, remember first lecture. Linear velocity and angular, so how fast you and in which direction do you go, and angular velocity, how fast do you rotate and around which axis. Okay, so those are vectors. Now consider alternatively a point. Okay, consider a point in Euclidean space. I say Euclidean space just to kind of like be clear what we're talking about. So if we have some other point O, then what we can do is associate a vector ROP, which points to point P from point O. Okay. So let me just draw it for you. So we have one point, and we have a different point here. Okay. So what we can do is we can draw a vector from one point, from a second point to the first. Okay. So this red arrow is a vector. Okay. So this red arrow is a vector. We can use it we can use it in our work. We can work with it as we work with any other arrows. It's just a, in 3D it would be just a three. Oops, sorry. It would just be 3 numbers. Okay. We could say the same thing about a point if we wanted. So we could say coordinates of each of those points represent a vector. But that would be completely equivalent to saying, okay, we have a coordinate system, and we'll associate with each point, for some reason I forget from where to draw them. We can associate with each point vectors like this. Okay. So if you want to tell me that, for example, each point already has coordinates, and those coordinates can be treated as a vector, I can in turn say that what you are trying to do is to discuss vectors pointing from the origin to those points. Okay. All of this is just words. All of this is just a way we express our thoughts. Like this doesn't entail some fundamental truth about reality or anything like that. But it's important to be clear what we are trying to do, right? So what I try to do is to claim that instead of talking about points as vectors, we talk about vectors that point from one, that are drawn from one point to another. And very importantly, those vectors behave like vectors, right? So once you start working with them, you don't ask from which point they are drawn. So a red vector here, you operate with it 3 coordinates. You don't drag along its origin. Okay, so this red point here, from which it was drawn, you don't drag it around. So in your expressions, you don't say, okay, we have a red vector, and we have origin point for this red vector. Those two are somehow part of the same thing. No, you just say you have red vector. Okay, so that is quite important. So for mathematical expressions, vectors behave like vectors. So they just have direction and length. They don't have origin. If you remember, like v, like this vector v here on top, it doesn't have origin. It only has direction and length. So are vectors like r, o, p. They only have direction and length. Okay. Right. That is, I think, quite important. But with those vectors r, o, p, it is useful to be able to relate them to geometry that I described. For example, this ROP, it is this red vector, like this guy is this red vector downstairs, right? And positions of point O and point P with respect to some origin, some other origin, might be those blue vectors, okay? So maybe there is some other origin, let's say we call it point A, okay? Point A. Okay, so with respect to point A, maybe O would have be described with this blue vector, and P will be described with this blue vector. Okay, so but we could denote it quite explicitly. Let's say that is R A O A P. Anyway, so what I'm trying to say is, for points, it is important to know if you're describing them as vectors. It's important to know with respect to what, with respect to which point, which other point. Okay. Okay. Is it? I don't know if this is clear or not. If any of you want me to explain it in some other words or giving some other example, I can. I don't expect it that this was completely clear. Right. It will hopefully be more clear as we do more of it. Okay. So notice, in order to find coordinates of a vector, you only need a basis. Okay. Remember last time we said that if you have a vector v and a basis, let's say b, in order to find coordinates P of V in B, if B is orthonormal, then all you need to do is to multiply V by B transposed, right? That's how you find coordinates of V in terms of basis P. Okay. That is for vectors. But for points, you also need origin. So if you have point A and you have basis V, basis, how do we make sure we don't conflict those names? Let's say we have still basis B. We have point point O. Let's say point Q and origin O. Okay. So first we find R U with respect to O, which we find as a distance from one point to another. Okay. And then we can find coordinates with respect to basis V for this thing as B transposed R OU. Okay. So for points, we have one extra step. It is insufficient to only speak about basis. It is important to speak about origin. Origin and basis together form what we call a frame. So a frame is three vectors, which form a basis. The basis has to be orthonormal. That is understood. It has to be orthonormal. And we visualize it as origin having as a frame having an origin. So let's just write it this way. So let's say this is Vx, this is Vy, and this is let's say Vz. And here we'll have origin O. Okay, so this is a frame. Frame, you can think about it as three vectors attached to a point, and this whole construction can kind of float in space, and you can attach it to like a rigid body, for example. Okay. 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 I think it can be quite confusing if you start to think about vectors as having points from which they point, and somehow frame with this origin point exactly presents this picture. Like it is three vectors, all of them start from some point O. It's just bizarre, especially when you have like some other coordinate system. Let's say, let me draw it. Especially if you have some other coordinate system here. And in terms of this coordinate system, this other coordinate system is translated and rotated, right? And the biggest problem here is that vectors are not even pointing from the origin. But remember, when we talk about vectors Vx, Vy, Vz, they're still vectors. So you can always just draw them, here. Oops. You can always just draw them here. That is always allowed. Okay. The catch here is that like this frame, it has additionally an origin. That's all. That is all. We kind of like to draw it the way I drew it, but bases, vectors that form the basis in the frame are still vectors. They're not some other new objects. In Russian textbooks in mechanics, sometimes they distinguish two types of vectors. that I think is I don't want to criticize the textbooks, but that might be just a mistake, methodological mistake, as in sometimes they discuss vectors like force vectors, which can be translated along some sort of axis. Then there are vectors that cannot be translated along axis, and then there are free vectors. All of this is just a like a way to confuse yourself. Vectors are vectors, just a collection, equivalent to R3 or Rn, if you want, or R3 in the 3D. Okay. So frame is an origin plus a basis. Basis is still consists of 3 vectors. Origin consists of 1 additional point. So you have to have 12 parameters to represent a basis. Okay, good. Any questions?
Origin can be anywhere, like not always. It is not always at 0, 0, 0.
No, absolutely not. Yeah, it can be anywhere. Let me just show you a small example. So imagine you have a robot. You have a joint, and at the end, maybe you have end effector, right? Maybe you want a frame associated with the end effector. So for that, you can attach the frame here. That would be a legitimate frame. At the same time, you might have a world frame somewhere else, like here, for example. Here, for example. Apologies. Right. And you can imagine those 2 frames are attached at different points. So there was 1 frame somewhere, or like world frame, what we'll call in just a minute, and then there's a frame here, right? Just 2 different frames, and they have 2 different origins. Any other questions? Okay, let us move on. Okay, so consider example. We know coordinates of a vector R sub OP in some basis V. Okay. And we know coordinates of some vector R sub OA, also expressed in V. Can we express this vector in V? So let's first just read this carefully, what I mean. So when here, what I imply by this notation, and it is always important to understand what the particular person implies. Like my notation will be different from notation in your other textbooks. It will be different from notation from your boss. It will be different from notation of your clients. It will be different from notation of some other use case you will find one day. Notation is never the same. So it is nice to try to have the same notation, but depending on having the same notation is just an error. Okay. You should always assume that you're dealing with non-standard notation. Okay. You need to double check. So what do I imply here? Well, what I imply here, I express downstairs quite explicitly. What I imply is that R is a vector that points from point O to point P. Okay. So let me demarcate it, I guess. This would be P. This would be O. Okay. So ROP is pointing at P from O. Okay. Analogously, ROA points at point A from point O. Okay. Okay, so the question now is, can we find a new vector that would point at a new vector that would point at A or at P from A? So what we want is this green vector here. Okay. So find a vector that points at P from point A. Sounds like a problem for I don't know, first grade in college. Is easy. Sounds easy. Let's try to see if we can solve it. Let's try to see if we can solve it. So first of all, we have just definitions of those things, right? We know what ROP is, P minus O. We know what ROA is, A minus O. Okay. From that, we can guess what RAP, P minus A, should be, and that is it is some combination of those two, which would give us P minus A. Well, we have P minus O. If we subtract from it O minus A minus O, minus O will go away, and we'll get P minus A. So the answer is. Let me give it a new. This, right? That is the answer. What we did here is equivalent to a change of origin. Okay, so originally both P was expressed with respect to the point O. Now we expressed P with respect to point A. Okay. How do we do it? Well, my suggestion is to do this type of reasoning. So you say, okay, what is each vector? Like OP is P minus O. So a difference between those 2 points. What is this vector? Or what is this? What is this vector? It is this. Now, you want to find this. You can come up with a way to manipulate those two to get it, and eventually you get this expression. Notice that final expression does not involve freestanding points. Those freestanding points, you can talk about them as coordinates with respect to origin, right? But that somehow just creates new entities. Like if you, for example, just express coordinates of P, coordinates of O, coordinates of A, and then do this whole arithmetic, effectively what you do is you abandon our vectors, ROA, ROP, and instead you create new vectors with respect to your origin of choice, which is fine. You just create more entities. Here, as you can see, we didn't need more entities. We could just work with the existing ones. And also notice, we knew those things, right? We knew those directed distances, so vectors. And they were sufficient to solve the problem. And somehow that is kind of like what I'm trying to say. We want to work with vectors, right? We want to work with vectors, and we need to remember what those vectors mean. So here is what they mean. This allows us somehow to come up with this formula. But the rest, the work with vectors themselves is quite easy. Right. All right. Now, if we want to express it in terms of basis V, all we need to do is, if we know this basis, is to, multiply this by V transposed, by whatever matrix that contains, whose columns represent this basis transposed, and we get this this thing. Do we have any questions here? Right.
Am I right that we started to think that vectors have a direction and some length, and then using several notations like R subscript AP or expressed in terms of V basis, we just intentionally add new information that we wanted to
Keep
not
track.
hold.
Yeah, keep track of. We want to understand what each of those vectors contains, what information contains, but it still is a vector. That is the important part. So this somehow contains information that the vector describes point P as seen from the point O. Okay, sure. That's what it describes, but it is still a vector, and you can manipulate it as a vector. That is important. And as abstract vector, so it's not coordinates with respect to some sort of a basis. It is just a vector. Here, on the other hand, we explicitly say this is coordinates of R with respect to vector, with respect to basis V.
So whenever we add this, I don't know how to call V on the left of this vector. So whenever we add that it is expressed in some basis, we already know that it's not just a vector, it's coordinates of a vector.
Yes, of course. That is what it means to be expressed in terms of a basis. It is coordinates. And coordinate vectors are always Rn. Any vector is equivalent to Rn, but coordinate vectors are just Rn. They cannot be anything else. Like you cannot be an arrow and be coordinates. You're just numbers. That is what it means to be coordinates. Okay. So all of this is words, of course. Like once you kind of like dive into linear algebra, you would see that being coordinates is just like being like input to linear operations, blah blah. Let's be clean about what we do. We will not dive into algebra. Instead, we will just be very careful. Like R here is a vector. It can be an arrow. Here it is expressed in terms of V. So therefore, it is a 3 numbers. That's what it is, 3 numbers. Okay, good. Good. And this is again called subscript, as far as like superscript, upper script, subscript. Wait, no,
I believe subscript is on the bottom.
Yeah, this is subscript. What is it? Superscript? Superscript? Upper script is okay with me. All right. Okay, now we go to a real kind of like mind-breaking example. It's something quite challenging. So we have point K, 2 frames, F1, F2, as well as something we called world frame. frame 1 is given by its origin O1 and basis T1. F2 is given by its origin O2 and basis T2. Okay. We know position of point O1 in the world frame. What it means is that we know its coordinates with respect to the origin of the world frame, and those coordinates are expressed in the world frame basis. Okay. So when I say we know position with respect to a frame, that's what I mean. We know the distance, directed distance from the origin of the frame to the point, and this directed distance is expressed in terms of coordinates in the basis of the frame. I understand that this sounds like complicated and technical, but this is what you would expect, right? Let me just for a second illustrate this point. So if I give you a frame and I say, okay, in this frame, you know the position of point O here, red dot. What you would expect it to mean is that there is this vector pointing from the origin of the frame to this red dot. And we know coordinates of red dot in terms of those green vectors. So for example, 1, 3, -2, right? So that is what you would expect. And that is exactly what it means. We know position of point O in the world frame means we know how far away it is from the origin of the world frame, in which direction, and this is expressed in local coordinates. Okay. And here is a vector that expresses position of O1. So notice it is a vector R. Subscript O1 refers to this point O1. I didn't name the origin of the world frame, so I don't put it in the subscript. In the upper script, we have omega, which is world. Okay. Now, basis T1 is given by matrix T1, whose columns are expressed as vectors in the world frame as well. So notice omega here. So we have for the first frame, we know its origin in terms of the world frame, and we know its orientation in terms of the world frame. So here, let me pause for a second and say something for the first time. We can say that T1 gives us orientation of the first frame relative to the world frame. So we can say it gives us a relative orientation. Why can we say that? Well, it will be clear, I think, from derivation later. But intuitively, you can think about it this way. You have some world frame, and you have another frame which says this frame has to be turned by T1, kind of like this, right? So it has to be turned, like, let's say, this way, right? That's what T1 essentially says. And the reason why it is a relative is because of this omega, right? It only says what T1 is relative to the frame of omega. Okay. So T1 gives us a relative orientation. Okay, good. And remember, what this matrix does is it has 3 columns. Each column forms part of the basis of T1. Okay. Now, we also know position of the point O2 in the frame F1. So we know O2 in the frame F1. Okay. And as before, here it is. As before, it is exactly what you would expect, right? You have you have the frame F1, right? This is the F1 frame. Let me denote it somewhere. And you have a point in this frame, let's say here, that is O2. Okay, O2. Now, you would expect this point to be, if you know position of this point, you'd expect it to be known in a sense of understanding this vector, which I just drew, which goes from the origin of the frame, which in this case happened to be O1, to this point O2. So you see this is like R from O1 to O2. And this whole thing has to be expressed in terms of the basis, which is for F1 frame, the basis is T1. So this vector, this makes perfect sense. What I'm trying to say is that there is a vector points from O1 to O2, and it is expressed in terms of basis T1. Okay. Sounds complicated, but that is, it's not very complicated in this case. Now, the basis T2 is given by matrix T2, whose columns are expressed themselves in terms of T1. Okay, so we know this with this matrix, but the columns themselves are coordinates in T1. So again, it is a relative orientation. It is a relative orientation how T2 second frame is oriented with respect to the first frame. Okay. So the task.
So, yes. But why T2? I mean, basis T2 is given by a matrix T2 superscript T1, whose columns coordinates of vectors forming. Why in the world frame?
Oh, that's a mistake.
If it's relative, should it be like F1?
Yeah, whose columns are coordinates of the vectors expressed in the frame F1. Yes, here should be F1. Good catch. Good catch. So the task is to express point K in the world frame while knowing its position in the second frame. So by now you understand this notation, right? I'm saying we know K with respect to point O2, and we know it in the basis T2. So it's indeed quite scary. Let me, for a second, draw this for you on a whiteboard, just like what we're dealing with. So first of all, let me maybe do it with vectors. So what we're dealing with is world frame first. That is the world frame. Then what we have is our two frames. We can think about it as a two-link robot, right? Oh, let me change colors. So we have our first point O1. Then we have our second point O2. Then we have our point K. Let's just note it. O1, O2, K. Okay. What are the frames that we are dealing with? So aside from world frame, we have F1 frame. Let's say it is kind of like this. Okay. Then we have our second frame. Let's say it is kind of like this. Okay. They are all orthonormal. I draw them kind of like iffy, but they are all orthonormal. So question is how to find K. If you know what you know, I will just draw it in black. What we know this with respect to the world frame. We know this with respect to first frame. And we know this with respect to the second frame. Okay. Well, that is what we have. We have those vectors with respect to different frames. Okay. Sound is that clear? Do we need any more explanation? No questions, right? Like now is a good time to ask questions. Well, we have picture. Okay. I'll go back. Okay. How do we deal with this? Well, let me show you how we deal with this. So there is a good kind of like strategic way to approach this type of problem. So first is express every basis in terms of the world frame basis. Like without thinking about what we have to do, just make sure that every basis is given in terms of the world frame basis. What we can call it, and what I think people call it, is getting absolute orientations. So before we had the relative orientation, frame 2 relative to frame 1, frame 1 relative to world. Now we can get absolute orientation. So everything relative to the world. So we already have basis T1 in the world frame basis, and that is T1 omega, right? Now, we know T2 with respect to the basis T1. That means by definition of what coordinates mean. So remember, we're not introducing new theory here. We always, the whole time, using only algebra of vectors. So we use material of the previous lecture without any change. So this is coordinates. This is a basis. How do we get original vector from coordinates in a basis? Multiplication. That's how. Multiply vector by matrix, you get the original vector. Or multiply coordinates by a basis, you get the original vector. The fact that we have not one vector here, but 3 vectors stacked horizontally, change nothing. Like can be 3, can be 20, doesn't matter. Operations on the columns are performed independently, right? If this somehow sounds weird, what I just said, remember how matrices operate. You have vector, 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 vector. If you multiply all of this, like all those vectors by a single matrix, what you need to make sure is that dimensions here is the same as dimensions here, right? And then multiplication is performed individually. Like this vector will be multiplied by this matrix, the whole thing, and it will produce you a new vector over here, right? Same with this one, same with this one, same with this one. Doesn't matter how many. So matrix multiplication can be seen as just a bunch of vector matrix multiplications stuck together. So there is nothing different here. All right, again, coordinates, basis, we get original vector. Notice we don't have a upper script. We don't have an upper script. We don't have upper script. So it means we are dealing with the original vectors, not with coordinates. Okay, but we can go back to coordinates, of course. How? Well, I skipped a step here. Let me show you how we can do it. So let me maybe clear everything. So we can multiply this whole thing by omega basis, right? Omega basis. What is the basis in omega? Well, let's say it is omega. Like omega is a basis in omega. Okay, so we can multiply by omega transposed this expression on the left, on the right. Omega is an invertible matrix, so we are in our rights to do so. And we will get this expression because this multiplied by omega transpose will just be t omega, so coordinates of t1 in omega. And this will be coordinates of t2 in omega, because those are free vectors. When you multiply them by omega transposed, you get the coordinates. So that's what is going to happen. So what we achieved in the previous slide, let me come back. What we achieved in the previous slide was we got a expression of the frame in terms of the frame T2 with respect to the world, right? So we had frame T2 with respect to the world. Okay. Now we know absolute orientation of the frame. Now we know absolute orientation of the frame. Okay. Now we what we can do now is express all vectors in the world frame. Express all vectors in the world frame. So we already know what position of point 01 in the world frame is. So we can express with the vector R01 is already expressed in the world frame. We also know vector from 01 to 02 expressed in the T1 frame, in T1 basis. So we can express this same vector in the world basis. How? Well, we get coordinate-free representation for this vector this way, right? What do I mean? Those are coordinates in T1. That is T1. That is coordinate-free representation. That is the power of what we studied last time. We see it for the second time today. So first we saw it here. Remember, coordinates, basis, coordinate-free representation of what we want. Now here again, coordinates which we are given, basis, coordinate-free representation. And as before, if we want it in world coordinates, we multiply it by omega transposed on the both sides, or whatever, like world frame transposed on the both sides, and we get this expression. Now, let me point your attention to one fact. We don't know coordinates of the world frame, right? We don't know anything about the world frame, how it's oriented, where the origin is. We don't know any of those things. We don't have to know those things because this first expression is just true. The second expression is just true, right? They're true irrespective of how world frame is oriented, right? So those expressions are true because of vector algebra, not because of orientation of the world frame. And notice that we don't have to have any information about world frame to evaluate this last expression. Like what we have here is a matrix we were given. That is a given matrix that we just know it. This is also a given. Like this we also know. So we multiply them and we get the answer. What I'm trying to say is you don't have to know anything about the world frame to evaluate this vector in the world frame. Okay. Now, we also remember that by definition, R from O1 to O2 is what we call O2 minus O1. Okay, O2 minus O1. And RO1 is by definition O1 minus O, where O is a world frame origin. Now we want to find O2 minus O. So point O2 expressed in the world frame. Well, how do we do it? Well, clearly, if you look at those two expressions and you want to combine them somehow to get O2 minus O, what you can do is sum them. So this plus this would clearly give you this. It just follows from definitions of them, right? Okay, that's what we do. We sum them. Here's a coordinate-free representation of the summation. Here is a representation in the world frame. Here is a representation in the world frame, but we replace our expression here with what we found here. Okay, and that is position of the second joint in the world frame. Why do we need coordinate-free representation? We don't need it. I just think, like, so far in this lecture, we never had to ask ourselves the following question. Given a vector in frame F1 or like frame 1 added to a vector which is only given in frame 2. So transform the first vector from frame 1 to frame 2, add them up, and express them in the frame one of the two frames. We never had to answer this question so far. And that is because we always do intermediate step with coordinate-free representation. So like this is always true. It requires no thinking about frames. But you cannot, for example, add this to this. That would be just incorrect. Hope I answered the question by Anton. Okay. Now, last part. We want to find K. Okay. So we're given position of K with respect to O2 in the frame 2. So in the basis T2. So first we use these coordinates to get a coordinate-free representation using T2. That is that is the basis in which it is expressed. Okay. Now we express this whole express this whole thing in the world frame. Okay. Next, what we observe is that this guy, we found him last time, I think here. So this guy is given like this. Okay. Now, what it means is that we have an expression of R of K with respect to O2 in the world frame. So if you remember our picture that I drew on a slide before, it had those black vectors, right? Those a few of those black vectors. First was O1, second was O2 with respect to O1, and the last one was K with respect to O2. Now we have all those black vectors, and we have them all with respect to world frame. Now it's time to try to use this information. So first, we know that K with respect to O2 is given by R vector, RO2K. Position of O2 is given by O2 minus O. So if we want position of K with respect to the world frame, K minus O, it is quite obvious that we need to sum them. We need to add RO2 to RO2K. Right. This is coordinate 3. This is in the world frame. And now all we need to do is to replace this guy with its definition, which is here. And we need to replace this guy with its definition, which is here. And that is the answer. That is the answer. So that is it. Do you have any questions about what I did here?
No.
Okay, good. Good. So what you should notice here is we have this. Let me go back maybe a little bit more. We have the procedure that goes kind of like this. First, express all bases in the world frame. So find omega T1, omega T2, right? All of those things. Okay, that is the first step. Second step, express all relative vectors. So positions of all origins in terms of world frame. So ideally find omega O2, you already knew omega O1, but right, those things. Alternatively, you can of course just deal with like those O1, O2, like intermediate vectors, right? And when you know all of those, your whatever vector you need to find, like you know, some K, RK, you just transport its own relative position to an absolute position, and you would add to this absolute position the absolute position of the origin of the frame in which it is expressed. When I say absolute position here, I mean you just express this vector in the world frame, and then you add to it the origin of the frame in which the point was expressed. That's it. So we start with orientations, then we go to origins, and then we go to a particular point. That is kind of the approach. Is that kind of, does it make sense?
Yes.
Okay. I understand that this is maybe a little bit boring, but so is you know, so is most of the studies. Okay. Okay. Now let us consider serial non-branching linkage. Ith link, so link number I, has a frame Fi attached to it. So coordinates of any points on this link with respect to the frame do not change. This is a subtle, subtle and maybe even like not really well put definition. What I'm trying to say is that imagine you have a link, let's say this microphone, right? Like a link. I attached to it like a frame, right? My hand is kind of like a frame. I attach it to it, and somehow any point on the mic will remain stationary in this frame, even if the mechanism somehow moves. Okay. That's what I mean. So attaching a frame to a link kind of implies that no matter how the mechanism moves, so no matter how the link moves, if some point was on the link, its coordinates are not going to change with respect to this frame. And the coordinates of a point with respect to a frame, remember, is the distance from the origin to the point, expressed in local coordinates, so in the basis. This makes sense, right? What I just said. Okay. So for simplicity, let us assume that the ith link, ith joint, by which the link is attached to the parent. Parent, let me explain again. So imagine that this is a link, right? This is a link, and this is a previous link, and this is a joint. Okay, this is a joint, this is a link, this is a previous link. Okay, so this will be parent link, this will be child link. So if it is joint number I, this is a link number I, and this is a link number I minus 1. That is if it is a serial chain without branches. There can be branches, they don't change anything significantly. I'm just giving you a simple example. Okay. So let's assume that the coordinates of this point in terms of the frame of this link, of the child link, are 0, 0, 0. Okay. It doesn't have to be. It changes almost nothing. We're just, we're just trying to be simple here. So, point O1, OI, sorry, point OI is a joint, and at the same time, origin of the frame Fi associated with the frame associated with this link, and the basis if Fi is Ti. So Ti is a basis, Fi is a frame. Okay. We can define vector O sub I plus 1, pointing from the current joint to the next joint. Okay. For the last link number n, we can define a vector RONK, which is a vector pointing from the joint to the end effector. Gripper, let's say, to the gripper. Gripper was what we have at the end of the robot, something that grips. Okay. So we know positions of those OI or I plus 1. So from previous joint, I need to somehow move away. So, okay, let's consider a simple example. So one joint, another joint. Okay, so one joint, another joint. So this is O1, O2, O1, O2. Okay, so we know those things with respect to the frame of this link. So like there's a link joint 1, link 1, joint 2, link 2. So O1, O2, this vector, we know it in terms of frame 1. Okay. And we need to find everything in terms of the world frame. By everything, I mean position of all joints and effector, orientation of all links, all this kind of stuff.
May I ask a question?
Yes, please.
If we define OI plus 1 in terms of frame TI, and we say that the origin of this frame is at 0, 0, 0, wouldn't that mean that ROI OI plus 1 is just ROI plus 1?
Yeah, TI is not a frame, it is a basis.
Basis. Okay.
Yeah, it's a basis. That is see, like I understand, like I have a suspicion that half the class, and by half I mean like everyone, thinks that I'm a little bit, you know, explain you like linear algebra for the first course and spending enormous amount of time on coordinates, but that is exactly why I do it. There is a difference between frame and basis, of course. Of course, what you said would be perfectly reasonable in the way you said it. Like you didn't make any mistake. It's just saying that this expressed in the frame doesn't make any sense. Because origin has no role to play when we discuss vectors. Okay? So when we discuss vectors, and this is a vector, remember, this is not a point, it's a vector. It makes no sense to talk about origin, because who cares about the origin in the vector? Vector is just 3 numbers, like an arrow. Doesn't have origin, doesn't have anything. It has direction and length. That's what it has. Okay. So in this case, what's going on here is you have R, which tells you how far next joint is from the previous joint and in which direction. Okay. And this information is expressed in terms of the basis T1, no, Ti. That's it. The joint, next joint probably is not going to coincide with the previous joint, but it can. If they coincide, it will be 0, 0, 0. If they don't coincide, it will be something else. Is it clear?
Yep.
Okay. I mean, you if you do a little bit of this by hand or in MATLAB or Python, you'll get it easy enough. It's like, this is not very complicated. So notation is horrible. Like notation is bad, while the operations themselves are simple. All right. So what we know is what we call it a relative position of the joints in local coordinates. And we know a relative orientation of the frames in local coordinates, right? I guess I didn't need to say in local coordinates in this case. Basically, what we know orientation of the next frame in terms of the previous frame. That is correct. That is correct. That is correct. By the way, here, let me draw your attention to one verbal fact. I say here exactly what I wrote. We know coordinates of the next frame in terms of the previous frame. In a different class, someone can tell you, we know transformation of the previous frame to the next frame. Transformation, okay? Did you catch what I just said? I could say we can have a transformation of the previous frame to the next frame. Transformation. So how do you need to rotate the previous frame to get the next frame? Perfectly legitimate, right? Let's say you have two frames, and you want to transform this frame into this frame. You have a linear operation that does it. And actually, it would be like if first frame is A, this is A frame. Let me make it in focus. This is A frame, and this is a B frame. So the transformation between them would be, as far as I remember, B transpose A, B transpose times A. That is transformation. And we even saw it last week. But this matrix B transpose A would have to be expressed in some sort of a basis. And not in just any basis, but in the same basis in which A and B are expressed. And then you can express it in a different basis. You can, for example, say, here's a transformation from frame 1 to frame 2, expressed in frame 5. And if this doesn't confuse you, it definitely confuses me. So, I mean, all of this can be worked out on the piece of paper, of course. Anything can be worked out on the piece of paper. But that is the reason why I don't give it to you, because like complicated for no reasons that I can justify. So here, what I say again is we have T1 plus Ti plus 1, so next frame, next basis expressed in terms of the previous basis. Okay, so we have next basis expressed in terms of the previous basis. That's what we have. Okay. Now let's solve this problem. We're not, like, it's a generic problem, so we're not going to like actually solve it. Like, I will just give you procedure. So first we start with rotations. We want T1 in omega. So what we have is first frame in omega, second frame in the first frame. Oh, sorry, second basis in the first basis, third basis in terms of the second basis, etc. So relative orientations, that's what we have. What we want is absolute orientations, absolute. So T2 in omega, T3 in omega, Ti in omega. The way we do it is we say T2 in omega will be coordinates of T2 in T1 multiplied by T1. We skipped coordinate free representation here because I think you get the idea, right? We could have said it is T2 equal to T1 times coordinates in T1, and then we say now we want coordinates in omega, we multiply it by omega transpose, and etc. But maybe you feel comfortable with what I just wrote here. So in this case, that is just the expression, right? T2 in omega will be equal to T1 in omega times coordinates in T1. Okay. Same for T3. It is coordinates of T3 in T2 times T2 expressed in omega. Remember here, don't make a mistake. Like, don't use here something like this. Okay, you have to have T2 expressed in word frame for it to work. Geometrically, this makes perfect sense. What you're saying is, here's absolute orientation of the second frame. Relative to it, we have a small rotation we need to do. Like, we have an absolute orientation, we need to do this rotation, and we get T3. Okay, it doesn't make any sense to say, oh, here is a small rotation that we need to perform to get from T1 to T2. Let me find T3 by multiplying, by rotating this small rotation. No, it's that makes no sense. All right, you need to work with absolutes. You need to work with absolute orientations. So you say this is how we need to change absolute orientation of T2 to get to T3. Yeah, sure, change it, but change absolute orientation of T2, not some relative stuff. So you always work with absolute orientations, and it is simple enough. So for ith term, you get coordinates in terms of the previous frame times absolute orientation of the previous frame. And that's it. You don't have to memorize any of this.
you can just derive it based on basic algebra. Okay, and it's a good idea to verify it, right? Once you derive it, it's very good to verify it. Okay. Now, thus we found absolute orientation of the link I, and is T sub I expressed in omega in the world frame. Okay. So once we know it, for the next basis, we just rotate it by a relative orientation, right? Or by a local basis, if you want. So it's rather simple, right? It is rather simple. You have previous absolute orientation. For the next link, it's relative orientation times absolute orientation gives you new absolute orientation. Okay. Okay. Questions so far? Good. Next, let's tackle translations. Translations is all those things where we have like those vectors O1, O2, or N, those things. We call them translations because if you want to like discuss operations as in how to transform this basis into this basis as an operation, if you want to discuss change of origin in this active terms, it will be translation. We often say that a different frame gives you a rotation and translation. Okay. Okay. Now, all vectors given to you in relative coordinates, we can transfer them to the world coordinates. Okay. We can transfer them to the world coordinates. How do we do it? Well, here's the relative coordinates. Here is the basis in which those coordinates are expressed. How do I know that is the basis? Notice superscript. That is, that is why. That's why we drag around all those upper scripts, and we get our vector in absolute coordinates. Okay. And then when we want, let's say, some point like end effector, what we get is the first joint plus distance from the first joint to the second joint plus from the second to the third joint, etc., plus from the last joint to end effector. And that's it. That's it. That's how we do it. We want center of mass, let's say, from of the ith link. We get the joint absolute coordinates of the joint of the link plus the relative position of the center of mass. We get expressed in the world coordinates, and we add it. That's it. So, and then at the end of the day, this is how we do forward kinematics for robots in terms of frame transformations. This one piece of the puzzle that we didn't discuss yet, but that is what you just saw is the crucial, most interesting part. Any questions about that? Okay, let's move on. So one question that you should ask probably is what to do with joints. Like so far we discussed frame transformations, not joints. So before we go to joints, let me remind you what rotation matrices are. So a rotation matrix is just a matrix that performs rotation around axis. So this, for example, is around x-axis by angle phi. This is around y-axis by angle phi y. This one is around z-axis by angle phi z. Okay. You probably remember them, so I don't need to spend too much time. Did you study rotation matrices, Tommy?
Yes.
Okay, good. So if you are so lucky that your joint is aligned with one of the principal axes, so your joint is aligned, let's say, with x or with y or with z, you can use a rotation matrix as your transformation. So when we were talking about relative orientations before, let me show you here. So relative orientations as in these guys, T2 expressed in T1, T3 expressed in T2, etc. Instead of one of those, you can use a rotation matrix around the correct axis, so around the axis in which your joint is oriented, and that would give you your transformation, and that would be your joint angle. So that is how you can how you integrate your joints. In usual practice, all for example, for something like a KUKA robot with all pin joints, they would all frame transformations, all of those T2 with respect to T1, T3 with respect to T2, all of them would be rotation matrices, because all of the joints would be aligned with principal axis. So let's consider that. So assume the ith link is connected to the previous link, where pin joint aligned with the x-axis of the previous frame. Then using our notation, we get that T with respect to the previous basis is equal to rotation around x. Okay, and we just note the angle as phi I. We call it parameterization. So we call it parameterization. That is the only kind of important conceptual moment here. So notice now this matrix has a parameter phi I. And this phi I is what we call a joint angle. So this is how much your joint rotated. Okay, this is how much it rotated. This is how much it rotated. Phi I. Phi I. And those phi i's are parameters. And we call it parameterization. Why parameterization? Well, for example, we could have used like Euler angles, quaternions, other things. In this case, it doesn't make any sense to use them. What makes sense to use is just I, this like one number, Fi, right? And that is a sufficiently good parameterization. If we had 3 rotations, like a spherical joint, let's say, maybe it would have been a different story. But for simple pin joint, doesn't make any sense to use anything else. All right. Now, sometimes it doesn't work. So let's say your axis points in this direction, where my finger points, and your joint is kind of like this. So they are at an angle, not at the right angle, at some angle, right? So first, what you can do is just multiply 2 matrices. One matrix will shift your x-axis into the direction of the joints, and second matrix will be your Rx matrix. So you can write it like this. You can again, what I suggest is this: you first change orientation of your basis so that a principal axis of your one of the principal axis aligns with your pin joint, and then you do the same trick as here. So then your local frame transformation, so your local change of basis, this local how your basis is oriented with respect to the previous one, is expressed this way. You have some sort of a transformation and then your rotation matrix, where this guy is constant. This guy is constant. Okay. So this guy, it may sound wild. You may ask me, like, what is this? How does it make any sense? I can answer you. This is your change of orientation of your links in the case when the joint angle is equal to 0. So put your robot into 0 position, and 0 position, you have to decide what it is. And if between your consecutive bases there is a change, then this change would be CI. This might be a point that you can understand what I'm trying to say, but you have hard time visualizing. It's okay. Don't stress it too much. All right. I think we are out of time for more examples, right? Or do we have time?
Yes, we are run out of time.
We're out of time. All right, good. Next time we will consider angular rotations in Jacobians. But before that, please spend some time thinking about what we just learned here. And if this somehow like makes sense, try to do it like in a, let's say, Python example or something. Just try to make sure you can do at least like for two-link robot, something like this. If it doesn't make sense, try to understand what exactly causes you problems. Next class, we would have more time for interaction. Like this was a still long lecture. Next time we'll have less material, hopefully. And I will give you time to ask questions. And try to, by the next time, make sure that you get through this. And, if you have questions, just ask them. All right. Thank you guys for finding time to attend the lecture. We'll see each other next time.
Goodbye.